Hello, and welcome back to day 3 of 2025. This should be a pretty quick one. I'm recording this on my lunch break here. So let's get into it. So for day 3, let's see. Our puzzle input consists of a rectangular block of a bunch of numbers, so a matrix basically. And we are supposed to maximize something called a joltage rating. And a joltage rating is basically you pick some subset of the numbers in a row, and then you kind of like concatenate the digits of the batteries that you've selected. And that gives you your total joltage. So here in the first row, we can pick 9 8 because 9 comes before 8. In the second row, we can pick 8 9 or 89 because 8 comes before 9, etc., etc. For part 1, we are just looking at exactly 2 batteries. So, we'll have resulting joltage rating for each row should be some number between well, if there's no zeros, let's say 11 to 99. And then part 2 ramps it up and says, okay, now we have, you need to select 12 batteries. So you end up with a 12-digit number after, selecting some number of batteries here. Okay. And then for the answers for part 1 and part 2, you just figure out the maximum joltage you can produce of the given number of digits for each part, and you add them all together and you get your answer. Cool. So let's take a look. We will be starting with the test input today. So test input is relatively small, and we can just verify. So if we do like row each unique, we can see that they're all the same size. So we can mix these together into a character matrix. And then because we only care about single digits, we can do execute each. And that turns everything into numbers. And then for reasons that will become apparent later, I'm going to transpose this. So our input, each column is going to be a row of batteries from our original input, and then each row in this matrix is going to be a position within our input. So let's assign this to P. Okay. So there's some important things to notice about the kind of problem description. Let's look at, we can select the leftmost column of P, and this will be the first row of our input. So first of all, when we're calculating joltage, we have 2 parts to the problem. We have to generate a 2-digit number and a 12-digit number, maximizing the number that we produce with some precedence rules, right? So the first number has to come before the second number, has to come before the third number in the input row, right? So first of all, we always need to produce a number of the required size. So, if we look at like the length of P, we can see that we're working with 15 numbers in total. So we should always be able to select, a 12-digit number. And certainly we can always select a 2-digit number. So there's no cases where, if we're looking for a 12-digit number, we select, 10 digits because a 10-digit number, no matter what its contents are never going to be greater than a 12-digit number, right? And then the second thing to notice is that when we are picking, let's say like the first number for our joltage here, we want the first number to always be as large as possible, assuming that we can still build a number with the required number of digits after that. So like, if we do 900, well, there's no zeros, so let's say like 911 here. 911 is always going to be bigger than like 899, despite the fact that we're picking, bigger values after the first number. If you maximize the first number, no matter what the contents of the rest of the array are, uh, you're always going to be maximizing your number that way. So this kind of hints at like, we could do a greedy sort of algorithm here, where basically the idea would be we go through, we pick the best possible starting number, and we calculate what the next number would be from there, and then moving on, we pick the best possible value for the second digit, for the third digit, et cetera, et cetera. So let's take a look at how we could solve that. So we have our first row and our inputs, and let's do a max scan. So when we do a max scan, this is basically like, okay, for every given position, what would the best first digit be, right? So max scan, just as the name implies, like scans through the array and outputs the maximum that's been seen at that point at every position, right? But there's a trick to this, because so our first number is 9, so it's always going to be the maximum. But we want to make sure that we don't pick 9 twice. Like basically, if 9 is in the first position, we want 9 to be the best. We want 9 to be the best first number for like the second position onwards. So we need to shift these best possible values to the right. One way that we can do that is by just dropping the last elements and then inserting some filler value into the front. I'm using -1, and I'll explain why in a second. And by the way, APL has circle style here, the dyadic form is rotate, which seems like it could work for what we want. The problem with rotate is that when you rotate to the right, the values that kind of like fall off on the right are added to the beginning, which is not what we want. We want to shift right. We want the last value to fall off, and we want we can fill in the first part with some filler value. Okay, now we can take our original. Well, before we do this, let's multiply this by 10. And this is basically just saying, okay, we have our best possible first digit values. Now let's shift that digit to the left, right? That's all that multiplying by 10 is doing here. And then we can take our original input here and we can add it. So we get this, and perhaps I can, let me do this. And transpose, so we get the original input on the top. So this first row here is our input, the first row of our test input, and then the second row is, the first digit will be the best possible first digit that could be at every position. All of them are 9s, which makes sense because 9 is in the first position. And then the last digit here is just the original digit from our input, right? And so if we look at this, it looks like the best possible value that we could get is 98, which is true for the test input. So I can just if we put this in like a function, and we run this on like W, I could run this for rank 1 on P, and then we'll do omega here as well. And what does this give us? Okay, yeah. So this is oh, this is interesting. Hang on. Is that right? Did I transpose P when I assigned this? I did. Oh, here's the problem. So now that we're working on oh, if I do this rank 1, I need to sorry, I need to transpose it here. There we go. Okay, so this is all the rows in our input, and this is like, you know, the one iteration of our function. We can just take the maximum across each of the rows, and we get 98, 89, 78, 92, which are the best possible values for our test input. And then we can just sum these. Oh, we're operating rank 1, so I have to do the sum out here. We get 357, which is the best possible value for our input there, right? Okay. Now, these operations that we're doing them, you know, this rank 1 operator here, we're sort of like operating on each row of the input simultaneously. But we actually, like, the operations that we're doing could apply to the matrix as a whole. We just have to modify a couple things. So instead of max scanning along, you know, the rows, we can max scan along the columns, and we can do the same thing that we were doing previously. And then append here, we'll use laminate so that it goes on top, like so. And this indexing here is why we transpose the input, because it allows us to easily, you know, drop the last row and prepend on the top there. And then we can do 10 times, right? And we can do P plus. Our input is already in the correct, you know, format or the correct shape to be able to do this. And then we just max sum along the columns and sum what we get, and we still get the correct answer. So we can operate on the matrix as a whole, basically solving all rows independently without having to operate row by row. Okay, so this is our answer for part 1. For part 2, we need 12-digit. We need a 12-digit number, but we're already in good shape. We can just turn this kind of like inner piece into a train, and then we can use the power operator, to iterate, you know, let's say like 11 times. And I'll take off the sort of answer preparation piece. We can look at the matrix. So we're doing, you know, the same function that I just described, except we're doing it 11 times, which results in 12-digit numbers at the end there. And you can see how these negative values kind of like percolate from the top to the bottom. And we have a bunch of values that are falling off, which makes sense, right? So, you know, once we've considered the first value in the sequence and sort of propagated that forward via max scan, there's no opportunity to use it again. Like, it's in the first position, so it can't ever appear in any other position. So by using the negative value, we kind of like discount it from consideration on future iterations. And then once we're considering the best possible value for the second position on the next iteration, we move that negative value forward. We've considered for the second position, you know, whether it should be the first number or the second number. There's no other places that it could be in our result. So once that negative number is there, we never, you know, consider it again. And then as for the values that are falling off here, this is kind of like, you know, this keeps us from, for example, if we had a really large number in the last position, we would never select it as our first digit, because there's no way that we could build a number with the required number of digits, if this makes sense. So yeah, we can do the same kind of max scan along the columns, add this together, and we get 312191 something, which for part 2 is our answer. And we can actually just like run this. So by making the number of iterations a parameter, we can construct a function and then run it for 1 and 11 times, which gives us our part 1 and part 2 answers simultaneously. And this is the entire solution for day 3. And if we look at this and actually consider our real input, just to verify that we're still getting the correct answers, we can paste this here. So we get 17,383, which is the answer for part 1, and 1726 ending in 203. Yes, that looks like the correct answer for part 2. So now the cool thing about this is because we are running, like basically we're operating on a single matrix, and we're not considering each row individually. We're basically like solving all the rows simultaneously. That means that it's very amenable to vectorization and all that good stuff. So this ends up being quite fast. If we look at how long it takes to spit out both of our part 1 and part 2 answers, we can see that is 320 microseconds, so less than a millisecond. And this is on a M1 MacBook, so I don't even know if this has... Dyalog's done a good job of Mac support, but I don't know if it has all the same vectorization support that you'd have on x86. So it could very well be faster there. But yeah, so like very fast. I haven't looked at what all the people writing this in Rust are getting, but I think 320 microseconds for getting both answers is very respectable. So this is the whole solution, 2 lines. Yeah, basically, what are the lessons? I guess consider the problem carefully. Don't do more work than you need to do. So in this case, thinking about the problem and the sort of constraints about what we're being asked to generate, you can figure out that you need to use some sort of greedy algorithm, and that would be fine. That can give you the correct answer. The other lesson, I suppose, would be to operate in large flat arrays as much as possible. And if you see an opportunity to, if there's multiple rows in the input, you see an opportunity to solve for multiple rows simultaneously or for all rows, then take it, because it's generally going to be very fast. Okay, so that is day 3. Thank you for tuning in.